In 1966, John von Neumann published a book, Theory of Self-Reproducing Automata, where he suggested that someday we could create a self-replicating machine. He suggested that we could send such a machine off to another planet and it could populate the planet with copies of itself. Many have fantasized about such a machine and a glorious day of exploration. However, in this video, I will discuss how such a machine would be built. This, of course, using our current technology, such as 3D printers. Bruce? Yes? Your other videos seem to be about evolution. Why the divergence? Ultimately, concepts from this video will enter into the question of origin of life. I see. Go on. When we consider a machine that can build itself, we often consider the 3D printer. Certainly, a 3D printer can print some of its parts. Could a more advanced 3D printer be able to print all of its parts? Stick it on a rocket, and we've got a von Neumann probe. Well, it isn't quite that easy. Let's look at my 3D printer. I can make all manner of shapes, but it prints in plastic. Plastic, of course, is made of oil from biology. Certainly using biological byproducts to produce the machine wouldn't work on another planet. But there are 3D printers that can print in other materials, including metals. You can print in aluminum, copper, steel, etc. These printers are technologically similar to mine, but rather than a print head, they usually place down layers of powder of the desired material and zap the shape with a laser, melting the metal into place. A 3D printer with the ability to print in metal and maybe other materials would probably be a better fit. But when the printer prints a part, the part must be assembled together with other parts to make a complete printer. We've got to have a robot arm, or maybe 2 or 3, to do the assembling. Robot arms must have a variety of attachable tools. The arm, the tools, and the 3D printer all need to be able to be made from locally sourced materials. Let's call these machines, the 3D printers, the robot arms so far, the manufacturing subunit. The next question, of course, is where do we get the materials from? The materials must be harvested from the environment around, but we don't find pure metals laying around. We've got to find the materials in their raw form and refine them. We will call this the materials subunit. So far, this subunit must be able to produce refined powdered metals from nature. Refining metals from nature is no easy feat. Usually it involves finely crushing rocks and heating them up to the melting point of the metal. That's a lot easier for aluminum than iron. But we've got to be able to get these metals from natural sources or our replicator won't do any replicating. Therefore, the materials subunit is essential. The first thing we note is that a blast furnace of some sort needs to be made out of materials that can withstand the heat. Clay seems a logical choice to me. So we need to be able to mine and refine clay. We also need to be able to manufacture with clay in the manufacturing subunit. That's actually not terribly hard. But as we look again at the 3D printer, we see that it uses motors, specifically stepper motors. To make stepper motors, we need to be able to make round things. We need to add a lathe to the manufacturing subunit. Or we could get creative and use a couple of robot arms to simulate a lathe. Stepper motors involve copper wire. Other metals such as aluminum, silver, or gold may be substitutable. But we need to make the metal long and very skinny. We need to extrude it. This is not that different than the plastic that comes out of my 3D printer, but we need to be doing it at the metal's temperature. Again, we will need to add the ability to extrude metal to our manufacturing subunit. Now comes a difficult one. The wire used to make stepper motors is enameled with a thin insulating film. This film is normally made of a polymer. Ooh, that's bad. Polymers are biologically sourced. So far, the only insulating material we have is clay. That would be difficult to work with as it is brittle. Insulating the wires will be a difficult challenge and will likely require updating our materials subunit. The wire is wrapped around an iron core. The magnets, iron, are used to complete the motor. Other metals simply do not have the magnetic properties of iron. Likely we will be forced to use iron. We also need to be able to magnetize it. As a coil of wire with electricity running through it produces magnetism, we may still be able to avoid iron. We really would like to because of the heat involved in melting iron. So far, so good. But without a computer to control our tools, both the manufacturing subunit and the materials subunit will just sit there looking stupid. So we need a computer. Building a computer is a different class of animal. The miniaturization required is incredible. Turns out, though, that for the manufacturing subunit, the computer can be rather simple. It reads instructions from a database, does some light interpreting, and sends the instructions off to the relevant motor. We may be able to get away with a computer that only reads data, not one that writes data or crunches data. The materials subunit, on the other hand, with its need to scout out sources, is likely to need a significant computer and a bevy of sensors. In any case, to begin making the computer, we will need some more materials. We will need silicon and doping agents to make P and N doped silicon. Silicon is a pain to refine, but it's got to be done. The materials subunit will need a serious upgrade. The P doping can use boron, aluminum, or gallium. We probably already have aluminum, so that's lucky. The N doping uses phosphorus, arsenic, or antimony. Did I mention a database of instructions? Our computer will be useless without them. Where the computer can be minimal, the instructions will be significant. We will need megabytes, probably gigabytes of data storage. Again, this will require alternative materials and miniature manufacturing techniques well out of the range of 3D printing. So we have to add a chip manufacturing lab to our manufacturing subunit. As current chip manufacturing labs are huge, this will be quite a challenge of miniaturization. And the instructions, while they will have to be robust, virtually bug-free, with failure management strategies, this is going to take a lot of work by a lot of highly talented software engineers. The code for the manufacturing subunit must contain every detail of every part and every action, but will actually be simple compared to that for the materials subunit. Do you see a pattern forming here? Every time we need something more, we have to extend the capabilities of other subunits. And every time we extend those capabilities, our information subunit has to grow right along with it, with high precision. But I think we're kind of done, don't you?
Where are we going to plug it in?
Plug it in?
It's got to be powered by something.
Oh, don't worry about that. We'll wait for a good electrical storm to zap it and get it going.
Is that going to work? Sounds like it'll fry everything.
Suppose you're right. So we need another subunit, the energy subunit. I think we can agree that our preferred form of energy is electricity, but the electricity will have to be much more disciplined than a bolt of lightning. There are many sources of untamed energy that we could tap. We could do solar or wind. We might be able to set up a water wheel. If we can find a good heat source, we may be able to build a steam engine, Stirling engine, or Seebeck generator. We definitely have multiple options, but at least one of these options must be implemented before our self-replicating machine can even begin to be tested. Our conclusion is clear. All 5 subunits, manufacturing, materials, computer, information, and energy, must all be fully developed before we have anything but a functionless work in progress. This would be a singular, unfathomably complex, irreducibly complex system capable of doing one thing, replicating itself.
Question: if one were to make such a self-replicating machine, would one have made life?
I think that by most definitions of life, that would be exactly what we have. If there is one feature missing to truly make it meet definitions of life, it would be evolvability. If I were coding the instructions for this device, I would begin by parameterizing everything. Let me explain. I define a box in my favorite 3D CAD software. I use a table of values for each dimension of the box. I now have a convenient number for length, width, height, and thickness. To make a box of different size, I just have to adjust these numbers. What if I created values for every dimension of my 3D printer? What if I judiciously made some values a function of others? Let this part be the length of 3 of these, that sort of thing. What if every time I copied the database to make a new generation, I twiddled with these numbers just a bit? Natural selection would filter out the poor choices, and who knows how things would look after 1 million generations. With the advent of artificial intelligence, we could extend this idea to more than just some dimensions. With some careful coding, this device could truly be designed to evolve. Wouldn't that be trippy? Now, would it be life? Our self-replicating machine would evolve. And what if we built this device and sent it off on a rocket ship to a distant planet? What if, whether with some software patches along the way or just by natural processes, the resultant replicated machines became sentient? What if they began to wonder about themselves and where they came from? I can just see an excited science bot writing up a discovery he made in the field. Lightning had struck a rock, melting copper in it. The copper had run down the rock like a little stream. The scientist had separated the copper stream from the rock and grasped with excitement that this copper was similar to the copper in his own motor's windings. This, he assumed, must have been one of the steps that nature took to put together the first self-replicating machine. He had made a leap towards understanding the origin of the only life he knows. But he would be wrong. And the team of engineers that assembled the von Neumann probe that first landed on his planet would feel insulted. They would feel robbed of the glory that they deserve for building such an amazing machine. Nobel laureate Dr. Christian Deveau said, "There may be a kind of threshold of complexity that must be crossed before life can emerge." Certainly this statement is true for human-made self-replicating machines.
But what's that got to do with biological life? Nothing!
In the next video, we will explore the similarities between von Neumann life and biological life. Please like, subscribe, comment, and share this video. Thank you.